go. 6.2. We're going to do sum and difference formulas. Okay? Now, don't quote me on this. I believe, I have to double check, they give you these formulas to use. I don't think you have to memorize. Okay? But again, I have to double check to see, because they do give you a reference sheet on your final exam. But it's just formula stuff. It's not like identities or anything like that. But our objective is we're going to apply sum and difference formulas for sine and cosine, and then we'll do the same thing for tangent. Okay? Once we get sine and cosine under our belt, tangent's actually just following the same pattern. And then we'll use these formulas to verify identities. There is one section in your book that we're not going to cover just because it's not really part of the standard that we need, and you don't need it for calc, so I just deleted it. I was like, no reason to kind of cover that stuff. So if you do look at the textbook in this section, you'll see it's like the last example I did end up cutting out. Even though I have all kinds of examples for it, but last minute deductions, it's gone. Okay. So, here we go. So I'm going to draw a quick picture here. Sounds like everyone's dying today. It's been like all day though, like all my classes. A lot of sneezing, a lot of coughing. Okay, so what I'm going to do is I'm going to create a formula, okay, and we're going to do cosine first, where if I take cosine of two angles added, what's that equal to? Okay, so I'll put it right here. So what I'm trying to do is this. I'm trying to find cosine of two angles added equals what? Okay? And it's not, and here's the thing, you can test it yourself. It's not the same thing as cosine of alpha plus cosine of beta. It doesn't work. Okay? So we gotta figure out, is there a way for me to come up with a formula or just something where I can evaluate that? Okay? And this is me doing that for us. So let's say we draw these two angles here. Okay. So we're on a unit circle again. Alright. So from here to here, this is alpha, this is beta, sorry. And then from here all the way to where A is, that's alpha. Okay? And my goal, okay, right now, and I didn't realize I started with subtraction first. We'll get to addition later. Okay. My goal is to figure out what is cosine of this angle here. Okay. So if I take alpha, the angle alpha, and subtract beta, what would cosine be equal to? Okay. So we got to figure out, to help us out, the distance from A to B. All right, we're going to start there first. So using just distance formula. So AB, we're going to have cosine of alpha minus cosine of beta. And then sine of alpha minus sine of beta. Okay, so just me applying the distance formula, something we've done in geometry and, well, pretty much all your math classes. We even covered it in college algebra, just for a brief moment there. Now I'm going to go ahead and expand that a little bit, okay? So I'm going to square this and this guy. All right, this is what we're going to get. I'm going to move it back a little bit, because as you can imagine, a lot of terms to write there, okay? So let's say if I square the first binomial here, I get the following. So cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. Okay, so that's just the first set of parentheses, me expanding. The second set of parentheses, it follows the same pattern, just with signs. So sine squared of alpha minus 2 sine of alpha sine of beta. I knew I was going to get out of space. You know what? We're doing it. There we go. Plus sine square root of beta. There it is. It works. Okay, now, this is a big mess. It really is. There's a lot going on here. So my goal is to see if I can, clean some of it up and possibly use some identities, okay? okay, that might actually help us out here. So let's look at the first part. I can use a different color. We have a cosine squared and a sine squared. So what is cosine squared plus sine squared? What's the identity that goes with 1? Yeah, so that sounds like a good idea to me. So let's go ahead and group them together. Okay, because we know that's going to be a 1. And then can you see the same thing with betas? Is there a cosine squared and a sine squared of beta? I think there is, huh? Yeah. Here, and oh hey, it's the one over here. So let's group them together, because immediately I know those are going to be 1s for us. Okay. And now we got the rest, which is this stuff here, which unfortunately, not much I can do currently with that. Beta. And then, yep, I'm going to have to use the other board. Darn. There we go. Yep. Okay, so now let's use the identity. So those are 1s. So 1 plus 1, I believe is still 2, right? Okay, and then we have, I'm going to rewrite this again. Typically, when you're trying to prove something, you don't want to skip too many steps. Especially when you have this many terms, you might want to, take the extra time and just show each reduction step. Textbooks don't always follow that pattern, especially grad school textbooks. Oh my gosh, the worst thing you can see in a textbook is this. That's like a death sentence. If you're trying to read a math textbook, you're like, how does this work? And you see the author do this. Proofs left to the reader. Great. I guess I'll never know. No. You end up figuring it out, but yeah, that's brutal when you see that in a math textbook, and they certainly do that. Okay, so this is what I got. Doesn't seem fun yet. I don't think I want to use that formula. Okay, so here's what I'm going to do. I'm going to try and clean this up even more. Okay, and this is how I'm going to do it. I'm going to repeat the same process. I'm going to move AB down to here. Okay, I'm just going to shift it. I'm going to make it the same length. Okay, I'm not going to change the length of it. Okay, so I'm going to move this. We're okay with green. Let's use green. Trying to make this a little bit easier to see, so we'll use green here. And, well, nah, let's draw separate. That's going to be ugly. It's going to be really ugly. Okay, so there's our normal. And here's this guy. So what I did is I took the exact same difference of those angles. I just moved it down here. Okay? So these are still the same length here. Now, why did I move it down to here? A couple reasons. First, because this is a unit circle, this point right here is 1, 0. That's easy to work with, right? 1s and 0s. Okay, so that's one of the reasons why I did that. The other reason is all my values are positive in this first quadrant, which again, easier to work with. Now, I could have taken the same distance and just applied it up here or over here. It's still going to get the same result. I just made it convenient for me to put it right there, okay? And what I'm going to do is the same thing. I'm going to find the distance here, which should be the same as this, just different values because we have the 1 and 0. And then set them equal to each other and see what it's all going to come out to. And it does come out to be a really nice equation, okay? So hang in there for the ride. We got a little bit more to go. Good news is the other formulas are a little bit easier. It's just this one takes a little bit of extra time. Okay, so I'm going to, we'll put it over here. So the new AB, okay, which is down there. So we're going to figure out what these points are. So this point here, is green, okay, is going to be cosine of alpha minus beta. And, man, I didn't space this out well, huh? This one's going to be sine alpha minus beta. and this is just 1 and 0. So now let's take these 2 points, put in the distance formula, and see what they give me. So we get cosine alpha minus beta minus 1 squared plus sine alpha minus beta minus 0 squared. So again, the reason why I picked that point specifically is because the 1s and 0s make the calculation a little bit easier to work with. Okay? All right, let's continue. So I'm going to expand the first set of parentheses. And just to save time, I'll show you what the result is. But you could do it off to the side if you want to FOIL it. You could do that, no big deal. Okay? So that's the first set, first binomial simplified. The second one, this is just sine of alpha minus beta, so it's just being squared. So this is going to be sine squared of alpha minus beta. Now, just like the last distance one, we can see sine squared and cosine squared pop up in 2 spots, and we know that's going to be a 1 for us. So let's use that identity again. Okay. So we get 1 here. Now we also have a 1 here, so that's going to be a 2 now. So it'll be 2 minus 2 cosine alpha minus beta. Okay. So now for my final step, because again, I drew it this way to where these are the same distances. I'm going to take this guy, set it equal to this, and see what is cosine of alpha minus beta truly equal to. Okay? And I promise you it does come out to be a nice formula. So let's do that for our final step. So let me exclude that stuff. All right, so we have 2 minus 2 cosine of alpha, cosine of beta, minus 2 sine of alpha, sine of beta, and 2 minus 2 cosine alpha minus beta. Okay, so we could square both sides, get rid of the square root part. First step, just get rid of the square root. Okay, second step, I could see that these 2 are gone. They're going to reduce out. All right. And I'm going to do, let's see, I'll do 2 separate moves. I was going to do it all at once, but that might be a lot. So I want this to be on the left-hand side, because usually when we see formulas, they're written that way. So I'm going to move this over here. Okay, and I'm going to move these 2 things over here. So I'm going to flip-flop their positions, okay? So this moves over by adding. So this will be 2 cosine of alpha minus beta. And then on the other side, positive, they're going to become okay. And then I notice that everything has a 2. So we can divide everything by 2. And voila, we got our formula. So if I have 2 angles, and I want to use cosine and subtract them, I can use this formula to figure out what's happening. Now, again, it doesn't seem like it's a necessary formula, but when we do some examples, you'll see why this is actually pretty cool. Also, math shout out. Good old Claudius did this one. Ptolemy. 2nd century mathematician. He did it with circles and chords. Okay, is how. Now his formula was an exact duplicate to this. There's a lot of course, with our symbols and variables, it's a little different than when he did it. But yeah, good old Claudius. Did a great job with it. So you can blame him. No, not really. Yes.
2 questions.
2 answers.
1, what's the sine formula? And are we going to talk about it anytime soon? Is it similar?
It is.
And 2, up there, top of the board.
Yeah.
Where's the cosine alpha minus beta coming from?
Okay, so it's this right here. Okay, so I'm saying that at this point, as I'm moving it down, it's these two angles being subtracted from each other. Is how I'm getting to that point there. So still, I'm still making this the same distance.
Yeah.
I'm just changing the points to where now I want to see what is this truthfully. And it came to this point here, which again, doesn't quite help me too much. So now that I know that these two distances are equal, because I made them that way. I made them the same distance. I don't know what the distance is. It's specifically, it's those guys there. To set them equal to each other to get to that point. Now, to find the other ones, we won't have to go through that extensively. Okay? It's actually a little bit quicker than that.
So is it alpha minus beta because you had to subtract by beta
Correct.
to get down to?
Absolutely.
Okay.
Yep. Now, can we find cosine of alpha plus beta? Absolutely. And here's how we're going to do it. So if you recall, well, I'll tell you what. I keep jumping ahead. I need to quit doing that. I just need to just go with what I wrote down here. So let's put here, by substituting the properties of even and odd functions, we can create the sum identity. Okay, so without me going through that whole process again, I can use properties of even or odd to figure out what the sum identity for cosine is. So this is what we got originally. Okay, so that's our original formula there. And now I'm going to swap out for a negative angle. In this case, we're going to sub negative beta for beta. Okay, we're going to let that be our negative angle in this case. So what's that going to look like? Okay, so me swapping out beta for negative beta. And you can see that that would be an addition problem, right? Subtracting a negative, which is what we want. Okay, so this would be cosine of alpha, cosine of negative beta, plus sine of alpha, sine of negative beta. Okay, so let's simplify. So we get cosine of alpha plus beta now, because we're subtracting a negative. Now, first set of terms, if you recall that a negative angle for cosine just results in positive cosine. So this whole thing just kind of stays as is. Over here, a negative angle for sine results in the whole thing being negative. So this is a negative sine multiplied by a positive sine, gives me a negative. So this will be negative sine of alpha, sine of beta. So there is the sum identity. Which again, easier to do with those properties than to go through that whole mess again, because you don't want to do that. Okay? All right, now, to save a little time, to figure out what sine and cos, or what sine is, okay? I'll just put some hints here, and I encourage you to maybe try it out yourself. But recall that sine is the same thing as cosine, oops, but just what, 9 degrees difference? 9 degrees to pi over 2. Okay, so we can use this. So we can use this to create the identities for sine. Man, I just put over there the worst thing you could see in a math textbook is proofs left to the reader. I just did that to you guys. I'm evil. That's not right. But we don't have much time, you know? Like, I want to make sure we can get through everything. So, again, I'll let that just sit there for a moment. If you want to give it a shot. But here's what the formulas would be for this guy. So sine alpha plus beta is equal to this. Okay. There's the one for there. And then we can use the even and odd properties to figure out what the difference would be, using the same process of what I did up there. So this will be sine of alpha, cosine of beta, minus cosine of alpha, there's the difference. Okay? Okay. That's me deriving them, which it takes a little time, but one of the things you're going to notice when you take a math class in college is professors do show you where these formulas come from, and I want to make sure you get used to it. It could be a little overwhelming. A lot of times it's one of those things where you just write things down and look at it later. It really is. Just because they do talk fast, and I know I probably talked a little fast there as well. But it's just good to know that it's not just some random formula, that it does come from someplace here. Okay, so here's what I'm gonna do. I'm gonna put both formulas right here at the top and just use as a reference throughout the whole examples. All the examples I'm gonna do. Using the formulas is the easiest part. Deriving them, it took a little work. Okay, so let's just summarize it. So I'm gonna put it right here. So if you wanna put them all together, you can do this. Okay, and then here's cosines underneath that we just did. Okay, so there we go. I'm going to leave that up there for the rest of the lesson. We don't have to worry about finding the whiteboard that has it, okay? Now, I didn't make an error. Notice that I have a negative and positive there, okay? Here's the reason why. When this is positive, this sign's going to be negative. When this is negative, the sign's going to be positive, so it flip-flopped. Okay, so that's why they write it in that format. Looks weird at first though, because we're so used to plus or minus, but we can flip it depending on if we need it in that context. All right, example. Find the exact values. So I got 2 examples for it. Now, I want you to notice something. Sine of 75 is not one of those exact values in the unit circle, right? We don't have it. So we got to think of another way to figure out what that is, which is why these are important. It allows us to figure this out. And here's how we're going to do it. You want to find 2 angles that we do know in the unit circle that add to 75, okay? So let's find that out first. So sine, so what 2 angles add up to give me 75, keeping in mind they're one of those angles in the unit circle? Okay, very good. So we're going to use 30 and 45, because we know what those are. Okay? Now that we have that in place, we're going to use the sum formula up here. So I'm going to write this down. So this is going to be equal to sine, okay, 30 degrees. So alpha is going to be the first angle. You could flip these, by the way, that's fine. But how I wrote it is how I'm going to follow it. So this is cosine of 45 degrees plus. Now let's finish out the formula. So it's going to be cosine of 30 degrees and then times sine of 45 degrees. Okay? And by the way, when I'm done simplifying it, that's what the sine of 75 is going to be equal to, without typing in the calculator or doing any of that stuff. Okay. So sine of 30, that's a half. Cosine of 45, square root 2 over 2. This is where the unit circle comes into play. Plus, okay, cosine of 30, square root 3 over 2. Sine of 45 degrees, square root 2 over 2. Wouldn't make sense to split up into, what, 60 degrees and 10 degrees, right? Because we don't know nothing with 10 degrees. So keeping it to those special angles helps us. Okay, this would be square root of 2 over 4. This is square root of 6 over 4. And then my last step, because they have the same denominator, we'll add it together. Square root of 2, square root of 6 over 4. There it is. There's the exact value of sine of 75 degrees. And again, you can check your work. If you type that in your calculator, And then sine of 75 degrees, they're the same. Which, that's awesome. I think it's really cool. I am out of space for part B, so we're going to put it over here. Same principle, except now I got radians. But that doesn't change. I'm still going to find two radian measures that add to give me 7 pi over 12. Okay, so we're going to do this one next. All right, so let's figure out what adds to 7 pi over 12. Now, if you think about it, we have nothing with pi over 12 in the unit circle. So it's not as easy as a degree measurement, but here's what I'm thinking. Okay, so I'm going to write it up here. So 7 pi over 12. I could write it as 4 pi over 12 plus 3 pi over 12, right? 4 plus 3. Now again, you don't have 4/12 and 3/12 on a unit circle, but when I reduce it, does that give me some values in the unit circle? It does. This gives me pi over 3 and pi over 4. We can use those, right? We can use that to evaluate. So keep in mind that when you see a radian measurement, you might have to split it apart. They might not look like things we can use, but when you reduce it, they can. Now, if I were to break this up into 6 pi 12ths and pi over 12, I get pi over 2 plus pi over 12. And we know that that's not a route I want to take. So this could take a little guess and check to make sure you get what you want. So let's do this. So cosine of pi over 3 plus pi over 4, which just to put in the back of your mind, that's the same thing as cosine of 7 pi over 12. Okay, they're identical. So we're going to use the formula. Now this is a plus. So look at what the formula says. Plus, we're going to put a minus in between them. Okay, so here we go. So we're going to have cosine pi over 3 plus cosine pi over 4 minus sine pi over 3 and then sine of pi over 4. Okay. Now, I will say, as you use this more and more, the formulas aren't too bad. You start remembering pieces of it. Let's plug the values in. So cosine of pi over 3 is a half. Pi over 4 is square root of 2 over 2. Okay, pi over 3 for sine is square root of 2 over, or square root of 3 over 2 times square root of 2 over 2. Now we can plug those values in. This is going to look very similar. Yes?
Why is there a plus between the two cosines?
Oh, thank you. There shouldn't be. Appreciate that. We get square root of 2 over 4 minus square root of 6 over 4. How about that? I think it's going to be that answer, but what? Just negative? That's what that's going to come out to be. There we go. There's the exact value of cosine of 7 pi over 12. Questions? As long as you have the formula, you just have to follow it. Okay. Now, what if I gave you this and you work backwards to figure out what that means? So let's do one example like that. Find the exact value of the expression. So this is a little bit working backwards here. So let's say you have cosine of 7 pi over 36 times cosine of 5 pi over 36 minus sine of the same angles. So we're going to work backwards. Now again, the purpose of this is to not use your calculator, okay? You can type all those in. And as long as you don't round, and you keep all those decimal values, you'll get the same answer I'm about to write. But again, there's a risk, because if you do round, you're not gonna get the exact value. So why don't we use the formulas over there to see if we can't find that exact value, okay? So we have 2 cosines, 2 sines. Which formula has 2 cosines and 2 sines? This guy, right? Okay. There's a minus sign there. So this is gonna be a plus sign for me, huh? See how I'm just trying to figure out which formula to use? So this is the same thing as, I'll put it here in parentheses. So this is a cosine of alpha plus beta. Okay, that's what this is showing right now, just by doing that comparison. So my alpha is gonna be 7 pi over 36, which that could have been alpha, it doesn't matter. This would be my beta then. Okay, so if you wanna put that down, I guess we could write that as an additional step. So alpha for me, 7 pi over 36. And then beta would be 5 pi over 36 there. So let's go ahead and rewrite things. So this is going to equal cosine of these 2 angles being added. Okay, so those are going to be equivalent to each other. This gives me a cosine of 12 pi over 36. This is going to work out nice. So that does reduce to cosine of pi over 3, which we know is a half. And there we go. Okay. I like that. I really do. Like, to be able to take something that seems complicated at first and to apply a formula that reduces it to something that we can find an exact value. That's pretty powerful in mathematics. It really is. Okay. All right, questions up to this point. So right now, you got 2 formulas that we're using to simplify something, okay? All righty. So let's try these ones next. Okay, I'm going to keep these up here, so we could just reference it. Let's try another example. Find the exact value of cosine of alpha plus beta given, now what I'm going to do in this example, I'm going to change it up a little bit. I'm going to give you some hints or just some guidance of what alpha and beta are in terms of other trig functions and see if we can't relate it to cosine, okay? So given that sine of alpha is 5 over 13, and tangent of beta is negative 24 over 7. For alpha is in quadrant 1, and beta is in quadrant 3. Nope, 2. Okay? So again, I'm giving you some hints about alpha and beta, and we're going to see if we can't use those hints to find this guy here. Okay? So we're being detectives. That's what we're doing right now. I don't know. See, I approach trig as one big puzzle. It really is. Once you start learning all the fundamentals, it's just using those tools to find some stuff. Okay, so what I would do first is, let's look at the formula for cosine of alpha plus beta. I'm going to rewrite it down here. So that's cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Okay, so that's the formula that I got there. All right, so I got sine of alpha, right? I'll check that off. They tell me that one. And I think that's all we got, huh? We don't have much. So we have to figure out what these other values are, right? Then we can plug it in, and we get our solution of what we want, okay? So how are we gonna do that? We're gonna draw reference triangles. Remember how we did that for inverses? The same process here, okay? So let me go ahead and draw those. Okay, so let's start with alpha. Okay, so alpha is in quadrant 1. So there we go. There's alpha, okay? So let's find some values for alpha here. And the only thing we know is this guy. I'm gonna box that out. So let's see, sine is opposite hypotenuse. So this is 5 and this is 13. And notice in my formula, I need cosine of alpha. So I need this guy, and I also need the adjacent side here. So I'll put A there. So once I solve for A, I can find cosine of alpha. Does that make sense? Okay, so we're again using different things to help us out here. So let's find A. So A is equal to, it'd be the square root of 13 squared minus 5 squared. And again, I'm just gonna save ourselves a little bit of time. We get 12 for that guy, okay? I'm finding this. Perfect. So I'm gonna put here that cosine of alpha is equal to 12 over 13. So hey, we have another piece of the puzzle that we figured out. Let's do the same thing for beta, because as you can see, I need cosine of beta and sine of beta to finish it up. So let's draw another little XY plane here. And beta is in quadrant 2, so we're over here this time. Okay, so there's beta. And all we have is this information on that triangle. Okay, so tangent is the opposite with adjacent. So we have here the 24, and then this would be the -7 part. But again, that's not gonna harm us in any way, the negative value. To find sine and cosine, I need the hypotenuse. So I'll put A there again. I'm gonna solve for A to get the hypotenuse, so I can find those two. Okay, so we get A would be equal to the square root of 24 squared plus 7 squared. And we get 25. Again, just kind of saving us a little bit of time. We get A to be 25. So now, I'll put here, cosine of beta is going to be -7 over 25. So I need the negative in this case because we are in quadrant 2. So it didn't matter for the A value, what I needed. It does matter for the trig value. And then sine of beta is going to be 24 over 25. So again, we're just using those reference triangles to find the bits and pieces of information I need. Now I can put it all together. Okay, I'm out of space on that board. I'll put it over here. Okay, so we're gonna have cosine, alpha plus beta. And I'm gonna go ahead and plug all those values in now. So this is what we get. So 12 over 13, -7 over 25, minus 5 over 13, and then 24 over 25. Okay, so now we got some real values that we can use. Okay, let's multiply them out. So we get -84 over 325, minus 120 over 325, which gives us a final answer of -204 over 325. Okay, so that's what cosine of alpha plus beta is going to equal to for us. Okay, so again, kind of using that technique from inverses to figure some of this stuff out. All right, questions? So speaking of inverses, let's include those. All right, let's mix those in just a little bit for the next example, and then we'll jump to tangent, and that'll wrap it up. So here we go. So we're gonna do the same thing, find the exact value of sine, and then in here I'll have the inverse of cosine, and the inverse of tangent. Okay, so now I have a little bit more happening here. I can figure out what that is. Now, again, with no calculator, we have to come up with a method. I mean, you can't type in the calculator and get your answer, but it's good to develop these tools now because they will be needed in the future. So what do I do? Well, here's the deal, okay? What I'm thinking is this. Let's let this guy represent one angle. And we've been using alpha and beta, so we're gonna let that be the alpha angle and let this be the beta angle, okay? And what I'm gonna do is draw those triangles again just for these two guys, okay? Once I have that done, then what I can do is apply our formula for sine of, is it addition? Yeah, of adding those two angles and find the exact value, okay? So that's what I'm gonna do. So I'm gonna let this be alpha, this whole thing, let that be beta, find out what they are in terms of what I need for this formula, and then simplify, okay? So let me write down the formula we're gonna use. Okay, so we're gonna use that formula there. And the reason why I know it's that one, because it's a plus sign, so we're matching with what this is. And I'm gonna need all these pieces of information, okay? So I'm gonna have two triangles, one with alpha in it, one with beta, find the values I need, and go from there. So let's do that. So this will be the alpha one. Okay, now we gotta be careful. Our cosine, if you remember, it's in quadrants 1 and 2. Okay, so I know because it's negative, it has to be quadrant 2. So up here, and this is alpha. Okay, so this will be the -5, this will be the 13 part. So the good news, okay, cosine of alpha, which I need, I already have that information I could do that with. But I also need sine of alpha, which I need the y value. So I'm just gonna put an A there. So again, we're gonna solve for A using a little bit of Pythagorean theorem. Okay, running out of space. So this, we have A is equal to square root 13 squared minus 5 squared. Okay, and we do get 12. I was trying to pick out values where the numbers come out pretty cleanly. Okay, so now we could say sine of alpha is going to be 12 or 13. And then we could say cosine of alpha is -5 or 13. Okay, so we have this and this. We got two things checked off that we need for this problem. And I mean, I put it this way, I know this is taking a little time to figure out this stuff, but it's stuff that we can do. We can figure this out. Let's do the same thing for beta. Now we have arctangent of 24/7. Now tangent works with quadrants 1 and 4, and because it's positive, we must be in quadrant 1. So here it is, and this will be beta, and this has to be 24, and this has to be 7. I'm going to put A there because we are going to need the hypotenuse to find cosine and sine, because they do need that. Okay? So Pythagorean theorem again. And this one come out to be 25. So it does come out to be, again, another nice number for us. So let's see, we need cosine and sine. So cosine of beta is going to be, 7/25. Positive, because we're in quadrant 1. Sine of beta is going to be 24/25. All right, need some board space. Okay, so now let's rewrite. So we got sine alpha plus beta. Okay, and now that I have all the values that I need, I'm going to substitute them. So the first one's sine of alpha, which is 12 or 13. Next one's cosine of beta, -5 or 13. Okay, cosine, beta, sorry, 7/25, let's say. Looked at the wrong angle. There we go. Then we get -5 or 12. And then sine of beta is 24/25. Okay. So now I actually have the means to figure out what sine of this stuff is. Okay, I actually can figure this out now. Multiplying together, we get 84 over 325, negative 120 over 325. We get negative 36 over 325. So that's what sine of that angle is going to be equal to. Okay? All right. Questions? So hopefully you can see it is building. It is building off of what we've done in the past, okay? With inverses, with just finding sines and cosines of those values itself, okay? So it does take a little bit of time to figure that part out, but once you have it, the rest of it just comes down to algebra, just rigor computation. Okay.